Imagine being the most perfectly engineered predator in the ocean. Self-heating eyes, a self-repairing blade for a face. A body so hydrodynamically optimized that evolution spent 55 million years stripping away everything unnecessary, scales, teeth, even certain fins, until what remained was essentially a living weapon. The swordfish is not a billfish. I know it looks like one. The long nose, the speed, the open ocean habitat. It looks like a close relative of the marlin or the sailfish. But put them side by side and the differences become impossible to ignore. A marlin's bill is round in cross-section, a spear. The swordfish's bill is completely flat, wide, sharp on both edges. Not a spear, a cleaver. That single difference tells the whole story. The swordfish belongs to its own family, Cepheidae, a lineage that diverged from everything else tens of millions of years ago and has no close living relatives remaining. It is, taxonomically speaking, completely alone. The only member of its entire family still alive, which, as we'll see, is weirdly appropriate. The fossil record shows that early swordfish ancestors first appeared roughly 55 to 60 million years ago, and they looked nothing like what we see today. Early forms had two elongated jaws, both upper and lower projecting forward simultaneously, almost like a modern needlefish. What exactly that double bill was used for is still debated. Prey capture, hydrodynamics, possibly both. Over tens of millions of years, the lower jaw gradually receded, only the upper jaw remained, elongating, flattening, sharpening. What we see today is the result of 55 million years of a single, relentless question. How do you kill things faster? Now let's talk about what that blade actually does, and how it survives doing it. The bill can reach up to half a meter on a large adult, and it takes an extraordinary amount of punishment. A fish weighing over 400 kilograms, moving at speed, swinging that bill hard enough to stun schools of tuna and injure large squid. Every single strike sends a shockwave back along the full length of the structure, concentrating right at the base where it meets the skull. Do that hundreds of times a day for years, and the mechanical fatigue alone should be catastrophic. But here's where it gets genuinely strange. When researchers analyzed the internal structure of the bill, they found a sophisticated gradient design. The tip, the point of direct contact, has the highest mineral density, rigid and hard, built to deliver maximum impact. Moving toward the base, the structure becomes progressively more porous and compliant, designed to absorb and dissipate shockwaves rather than transmit them straight into the brain, hard at the front, flexible at the base. No obvious weak point, and stranger still, when scientists looked at the cellular structure of this bone under a microscope, they found almost nothing. In most vertebrates, bone is full of cells called osteocytes, the supervisory layer that detects microdamage and coordinates repair. The swordfish bill contains almost none. The lacunae, the tiny spaces where osteocytes normally sit, are empty. Scientists call this a cellular bone, and for decades it deeply confused bone biologists. How does a structure under this kind of mechanical load repair itself without the cells responsible for repair? The answer came from examining broken bills, and broken bills do get repaired, systematically, in a process that closely mirrors fracture healing in mammals. The bill retains osteoclasts and osteoblasts, the cells that break down and rebuild bone tissue. What it lacks is the centralized supervisory layer. The repair system is decentralized, and it works. The implications extend well beyond fish biology. If bone can self-repair without osteocyte oversight, it raises fundamental questions about skeletal healing in vertebrates, and may eventually open new directions for treating bone disease in humans. The swordfish, entirely by accident, has become a research model for one of medicine's most important questions. Now, the deep ocean. Most large predatory fish are creatures of the sunlit zone. Warm surface waters, plenty of light, conditions where muscles fire at full capacity. Swordfish treat the surface as a launching pad, something to leave behind. Electronic tagging data confirms that swordfish regularly push past 500 to 900 meters during daytime dives, and that's not even the ceiling. The deepest recorded dive sits at 2,878 meters, nearly 2 miles down, where sunlight is completely absent, water temperature drops below 5 degrees Celsius, and pressure is crushing. The only light at that depth comes from bioluminescent organisms, cold flickers in absolute darkness. This is not an environment a large fish was built to function in, and yet the swordfish goes there to hunt. The reason it can sits in its eye muscles. In most vertebrates, the eye is controlled by 6 small extraocular muscles that rotate and position the eyeball. In the swordfish, one of these muscles has undergone such a radical evolutionary transformation that it barely resembles muscle tissue anymore. Its sole function is to generate heat. Scientists call it the heater organ. densely packed with mitochondria and blood vessels, burning energy continuously to produce warmth. Surrounding it is a countercurrent heat exchange system, arteries carrying warm blood and veins carrying cold blood running side by side in opposite directions, recycling warmth before it can escape into the surrounding water. The result? A swordfish's eyes and brain are maintained at temperatures 10 to 15 degrees Celsius warmer than the seawater around them. In practice, this means that while the swordfish's prey is slowing down in the cold, reactions becoming sluggish, vision degrading, the swordfish's visual system is still running at full speed, sharp enough to detect the faintest flicker of movement from a fish or a tentacle in near total darkness. This is an evolutionary weapon sharpened over tens of millions of years, and it is precisely this advantage that sometimes brings swordfish into encounters with giant squid, animals that can reach 13 meters in total length, carry the largest eyes of any creature on Earth, and wield tentacles lined with hundreds of razor-edged suckers. No one has ever filmed what happens when these two animals meet at depth. But circular scars on swordfish bodies, the unmistakable signature of squid suckers pressed into skin, suggest the encounters are not always clean. Here's the part of the swordfish story that I keep coming back to. This animal is a marvel of optimization. Self-repairing bill, heated eyes, oil-lubricated skin. A gland near the base of the bill secretes oil that is actively pumped to the surface through tiny pores, reducing drag by over 20%, and the speed. You've probably seen the number 97 kilometers per hour quoted somewhere. That figure has been circulating for decades, and scientists have been skeptical of it for just as long. When researchers actually modeled the biomechanics, the realistic ceiling came out considerably lower, somewhere between 36 and 50 kilometers per hour. The hard limit isn't muscular, it's physics. Push fins through water fast enough and the pressure drops so sharply that the water itself starts to vaporize, a phenomenon called cavitation, releasing pressure bursts powerful enough to destroy soft tissue. The ocean sets the speed limit, not the fish. But let's put even 50 kilometers per hour in context. That is a creature weighing hundreds of kilograms, maintaining that velocity through a medium 800 times denser than air, while swinging a self-lubricating blade that accounts for a third of its body length. The heater organ runs constantly, the deep dives happen daily. The hunting never stops. The result is chronic energy stress. And that pressure produces an inevitable consequence. Adult swordfish live completely alone, not by preference, by mathematics. A single mature swordfish requires a large enough hunting territory to meet its caloric demands. Two in the same stretch of water means neither gets enough. So outside the brief window of spawning season, eggs and sperm released into open water without prolonged contact, swordfish live and die in total isolation. No pod, no group, no safety in numbers, just the ocean, the prey, and the blade.